So welcome to our Freshwater Stewardship Community webinar series. We're happy to have Claire with us here today as our keynote presenter. And then we also have two members of our Watersheds Canada staff. My name is Nicole. I'm the environmental technician at Watersheds Canada. And we also have Monica, who's the communications and fundraising manager. And Monica will be able to help you if you have any tech problems or if you have any questions. You can feel free to send her a private message. And now a little bit about Watersheds Canada. We're a nonprofit and charitable organization based in Perth, Ontario. We deliver programs across the country in partnership with landowners, community groups, and students who are looking to take action to protect their freshwater. On the screen, you can see some photos of our different programs. So on the top left, we have our Natural Edge program, and that's where we worked with landowners to naturalize their property using native plants. And then on the bottom is a photo of our Love Your Lake program, which is delivered in partnership with the Canadian Wildlife Federation. And it's a shoreline evaluation program where we fill out an assessment for each property on a lake. And each property owner gets a custom recommendation with voluntary actions that they can take to help protect the health of their lake. And then finally, on the right-hand side, you can see our fish habitat restoration program. And in that photo, we've got a brush bundle, and brush bundles can help promote the health of wildlife populations and improve water quality in lakes by adding woody debris. And so if you have any questions about these types of programs, feel free to drop them in the chat, or you can also send us an email. And we're all here today because of one of our initiatives at Watersheds Canada, which is the Freshwater Stewardship Community. And the Freshwater Stewardship Community has over 1,300 members from 7 countries. We have 19 webinars and 15 handouts archived on our website, which is watersheds.ca/freshwater-stewardship. So I would encourage you to check those out after the webinar to see any that you've missed. And we'd also like to thank the Peterborough K.M. Hunter Foundation and the S.M. Blair Family Foundation for their funding support this year for the freshwater stewardship community. And I also just wanted to let you know about our next webinar that's coming up. And so that is the plastic pollution in the Laurentian Great Lakes, what we know and how we can act. So that one is taking place on June 14th at 1 p.m. And it's also part of our free Rivers to Oceans Week programming. So I really encourage you to check that one out. Monica will drop the registration link in the chat. So once again, it's at watersheds.ca/freshwater-stewardship. And I also wanted to highlight the handout that we have that goes along with this presentation today. So we've taken some of the things we'll learn today and also added additional resources with more information for you to see. And that will be emailed to you a couple of days after this presentation, along with a recording of this webinar. So that's something to look forward to. And finally, I'm going to introduce our speaker for today. Claire Herbert is the data manager for Canadian Watershed Information Network and the program manager for the Manitoba Great Lakes program at the Center for Earth Observation Sciences at the University of Manitoba. She has spent her 20-year career conducting freshwater ecosystem research in Canada and overseas, focusing on the effects of climate change on in-lake processes and remote sensing of algal blooms on prairie lakes. As data manager for CanWin, Claire works with a global network of collaborators to make freshwater marine science open and accessible. So as we go through the presentation today, if you think of any questions, you can just feel free to save them, and then Claire will answer those in the question and answer period at the end. So as you think of them, you can type them in the chat, and then we'll answer those all at the end. And with that, I will pass it over to you, Claire.
Thank you, Nicole. I'm very pleased to be here. So thank you for inviting me to share some of the recent work I've been doing. So I have introduced myself a little bit in my slides, so I'll share my screen straight away. And most of my career was spent looking at the in water components, so looking at the algae and looking at actual chemistry, water quality. And then when I moved to the Center for Earth Observation Science, that's where I was able to marry my love of water quality work with looking at how we can measure water quality using satellites. So I think that should be the right screen. So I work at the University of Manitoba in Winnipeg, Manitoba, and the university is located on Treaty 1 territory. So the University of Manitoba campuses are located on the original lands of the Anishinaabe, Cree, Ojibwe, Dakota, and Dene people, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. At the university, I work in the Center for Earth Observation Science, as Nicole said, which is within the Faculty of Environment, Earth, and Resources. CEOS is a leading multidisciplinary and collaborative research center focused on understanding how the Earth will respond to climate change. CEOS researchers conduct their fieldwork all over the world. However, the Arctic freshwater marine system is a unifying focus of activity because climate change affects this region more acutely than anywhere else in the world. Our Arctic research is also one of the 3 signature research areas for the university. As Nicole also mentioned, I wear a few hats. So I manage our open data research portal, and I also manage the Manitoba Great Lakes program, which is a program that is led by researchers at CEOS and is a multidisciplinary collaboration dedicated to conducting research and providing data for science-based decision-making in the Hudson Bay watershed. Now, we live in Canada, and Canada has thousands of lakes, more than any other country in the world, with over 500 lakes that are larger than 100 square kilometers. The province of Manitoba, where I conduct my research currently, contains over 5% of Canada's freshwater and is located within the Nelson River watershed, which covers 4 Canadian provinces and parts of 4 United States. In Canada, the watershed covers over 1 million square kilometers alone. This watershed includes a series of interconnected large lakes, which you can see on the left here. So they are Lakes Winnipegosis, Lake Waterhen, and Lake Manitoba. And I'm going to refer to these in my presentation as the upper MBGL. So these lakes feed via the Fairford River here into Lake Winnipeg. And Lake Winnipeg is the only outlet into Hudson Bay, connecting the Nelson River watershed to the Hudson Bay watershed, within which freshwater and marine systems meet and are transformed before flowing into the Arctic. Moreover, the upper MBGL filter nutrients and carbon exported from agricultural and urban sources before they can reach Lake Winnipeg. However, the physical, chemical, biological, and geological processes that are occurring in these lakes are still not well understood. Therefore, we have a poor ability to predict the responses and understand the effects downstream to Lake Winnipeg and therefore Hudson Bay. This leads to lake management and governance being decided without adequate scientific support. Now, as I said, the watershed we live in is huge, and over 5.5 million people live within this Nelson River Arctic watershed and depend on its freshwater resources for many ecosystem services. Indigenous and Métis organizations have developed one of the largest freshwater fisheries in North America. Walleye, whitefish, and goldeye provide millions of dollars to the local economies from industrial fishing, and of course, the sport fishery is also a significant economic driver for local economies. Manitoba Hydro harnesses green energy from a large, fully managed hydroelectric system that spans most of the central and northern portions of the Great Plains of North America. Local communities, Indigenous organizations, and small-scale businesses rely upon stable water quality and quantity to meet their requirements for drinking water, irrigation, industrial use, and recreational activities. A common thread, however, that I hear when I speak to concerned communities within our watershed is concern about the health of their water. Issues that come up consistently include concern about the amount of nutrients like phosphorus and nitrogen in the water, algal blooms and watercolor, or turbidity, as it's sometimes called, and how these factors relate to drinking water quality and affect fish and human health. If you saw Lemissa's great talk, also hosted by Watersheds Canada, you have already heard about algal blooms and issues surrounding them out east in Lake Erie. I'm going to focus on two of those constituents, specifically the algae and the watercolor or clarity. So algae are important as they are the base of the food chain, but too much algae or the wrong type can be harmful to humans and wildlife. In too high of a concentration, algae can cause blooms that cover lakes with a green or blue-green layer, which looks unappealing. And if the algae are cyanobacteria, they can produce toxins. In addition, when the algae die, they decompose and use up oxygen in the water, which can create low oxygen conditions harmful to fish and other aquatic life. Because algae need nutrients like phosphorus and nitrogen to grow, we can use the amount of algae in the water as an indicator of the level of nutrients in the water at specific points in time. The type of algae can also tell us if nitrogen or phosphorus is a limiting factor. For example, if blue-green algae are dominant, we know that likely nitrogen is available in limited amounts, as some blue-green algae can fix nitrogen from the air and therefore outcompete other algal species. So in this image, you'll see on your left a bloom that happened on Grand Beach in Manitoba on Lake Winnipeg, and on the right are just some different species of algae that occur in Lake Winnipeg. Now, watercolor is a measure of turbidity in a lake, or water clarity. When we measure turbidity from a water sample, we are looking at the amount of dissolved and particulate or solid particles in the water. Light from the sun can be blocked or scattered by these particles. The particles that make water turbid include algae, plants, different types of soil particles like silt and clay, and salts, minerals, or metals in the water. Turbidity can be caused by many things, from high precipitation events like rain or snowmelt that cause runoff from the land into the water, to activities such as dredging, construction, or agriculture. People tend to see blue water as good quality water and green water as enriched or poor quality water. And brown water comes from organic runoff, such as runoff from soils. If water changes from blue to turbid, so from more light blue to brown or green, it can negatively impact fish and other aquatic life, as higher turbidity can block out the light that plants need to grow, reducing the amount of food available to organisms like zooplankton. Higher turbidity can also make it harder for fish to see and catch their prey. If soil particles such as clay or silt are causing the turbidity, they can clog the gills of fish and bury and kill fish eggs. These particles can also carry pollutants and harmful bacteria into the water body. So physically traveling around the prairies to collect water quality data is time-consuming and expensive. So you can see here, this is my research area. So to travel to the north end of Lake Winnipegosis here, from Winnipeg, where I live, takes over 6 hours, and that's without stopping to actually take any water samples. The sampling program I will discuss later briefly, where we sample these lakes here, Winnipegosis, Waterhen, and Manitoba, during the spring, summer, and fall seasons, cost us just over $3,000 Canadian for gas, food, and lodging, which was mainly tent camping, to sample 3 times in 1 year. That does not include the cost of sample analysis, research time, etc. So in a country as large as Canada, how can we collect the information we need to help communities understand their water body health in a long-term sustainable manner? So that's where working with satellites comes in. And I'm going to begin by giving you a brief overview of what light means in the context of remote sensing. So the sun emits energy in the form of photons. These photons travel at different wavelengths, which are measured in units called nanometers. Humans can see in the visible wavelength or spectrum from 400 to 700 nanometers, which we see as different colors. Once the sun's light reaches the atmosphere, its path may be changed based on whether it is reflected or passes through constituents such as water molecules in the air or particles that it meets. If the light passes through the atmosphere, the photons are either scattered or absorbed by something on Earth. So the photon can be absorbed by a variety of constituents, including those such as algae that we want to monitor. So in this diagram here, you can see the A stands for absorption and the B stands for constituents that make up backscattering values. So the constituents in the water that absorb photon or light are algae in terms of phytoplankton, so the APH, non-algal particles, which are ANAP, such as sediments, dissolved organic matter, ACDOM, for example, constituents that have dissolved off particles like sediments and water itself. And so you will no longer find them if you filter the water and look at just the filter paper. And water itself, which is the AW. If the photon gets scattered in the water, it will either scatter forward deeper into the water or backwards towards the surface, where some may be re-emitted. If the photon is re-emitted, it can be detected by a sensor on a satellite. Anything that causes absorption or scattering of the light is called an inherent optical property. Satellites carry instruments with sensors that can measure many different constituents depending on the instruments. Later on, I will mention a few satellites that are commonly used to look at water quality. The satellites measure the amount of reflected solar radiation, as I said, or photons, at specific wavelengths. The satellite I use carries passive detectors, meaning that they only detect what is reflected back to them or emitted from the land or water. So the amount of light absorbed or scattered by the different constituents in the water govern the color of light the satellite sensor sees. When the satellite receives the signal, it transmits it to a ground station where the signal is processed and converted into an image. We use step-by-step recipes or algorithms to translate what we see in the images into measurements of what we're interested in, such as algal concentration, where we're using chlorophyll as a value, or turbidity. The algorithms are based on the relationship between what is in the water, which I call those inherent optical properties, to what is emitted from the water, which are called apparent optical properties on your right. This relationship is called the remote sensing reflectance and is defined in the formula that you see on the right there. I'm not going to go into any detail about it, but one term commonly used in remote sensing is called radiance. And radiance is the variable directly measured by the satellite. So essentially how much light the satellite sensor sees from the object it is viewing. And it includes reflectance from clouds, which is another factor we have to be aware of when we're analyzing satellite data. So radiance is a unit value usually shown as watts per steradian per square meter. So the algorithm that you see there, the remote reflecting sensing, simply shows us that the value of the constituents from the backscattering divided by the sum of absorption and backscattering values is equal to the water leaving radiance divided by the amount of light hitting the surface. So, as I have mentioned, remote sensing algorithms rely on those specific optical properties of the constituents, which we are sometimes able to see with our eyes. For example, we see leaves as green in summer because they strongly reflect green light. Not all important wavelengths are visible to us, however, but they are visible by a variety of sensors. The satellites we use allow us to use the signals measured by the sensors and convert them to the radiance values I just mentioned, as well as reflectance values, which are percentages. The reflectance is the ratio of the amount of light leaving the target to the amount of light hitting the target. And I use the Sentinel-3 satellite for my work. So the key thing here is just to know that everything's based around this RRS algorithm. So this is just a brief overview of the Sentinel-3 satellite I use. There's actually two satellites in orbit, 3A and 3B, and they have an identical orbit with what they call a phase shift of 140 degrees. So the satellite 3A has been in orbit since February 2016, and satellite 3B has been in orbit since February 2018. And you can see that the satellite itself contains many different types of sensors. And the one that I'm interested in is the OLCI, or Ocean and Land Color Instrument. And that instrument has 21 different bands or wavelengths that it measures. And those bands are of different widths or nanometers. So that allows the satellite, the two satellites, to have a resolution of 300 meters and a revisit frequency of 1 day, which means they travel over the entire Earth in 1 day, which gives us very excellent coverage. Now, there are other excellent sensors for satellite work, depending on what a user wants to do and what water body they're working in. So just to give you an idea, NASA's put up quite a few satellites. So the most recent one is the Terra and Aqua missions, which carry a MODIS sensor, which is the one we use for water quality. And you can see there's other sensors on there as well. And this sensor on the, or this satellite on the right, is actually developed by the European Space Agency, and it's called MARIS. So the MARIS sensor operated from 2002 to 2012 as part of the ENVISAT mission. And the Sentinel satellites, the OLCI sensor that I use from the Sentinel satellites, is considered the continuation of the MARIS satellite imagery collection. Other satellites that have been in operation for a long time in different forms are the Landsat satellites by NASA, which have been operating in one form or another since 1972, and there are plans to release another satellite, Landsat 9. In addition, NASA is going to be releasing a plankton, aerosol cloud, and ocean ecosystem mission, where they are specifically looking at a broad range of wavelengths at a high resolution. And the main instrument on that is also the OLCI instrument. So when researchers started conducting work using satellites, the majority of the work was conducted on the ocean. The ocean, however, is much more transparent than many lakes and does not usually contain a lot of constituents other than algae, which can cause absorption or scattering of the light. These waters were eventually assigned a classification of case 1 waters, meaning they are not optically complex. Freshwater lakes, however, are usually very optically complex. They often contain solid or dissolved particulates that can color the water or scatter or absorb particles, as well as phytoplankton or algae, which can cause large blooms. These are called case 2 waters. And so those are the waters that I work on. In Canada, there has been a lot of work done on case 2 lakes, where algae in the summer are dominated by species that form surface blooms. So this is an image from the 2000s on Lake Winnipeg, and you can see we call them grass clipping formation of algae on the surface of the water. And those are easy to see from a satellite. However, the Manitoba Great Lakes are physically and chemically different than the lakes to the east of them. And therefore, in order to understand the current ability of satellites to accurately calculate those algal concentrations or turbidity, we must also collect water samples and use other equipment to compare the spectral signature we see when we are on the lakes to what the satellites see. So the purpose of my work in remote sensing is therefore to study the characteristics of reflectance spectra during seasons, to evaluate remote sensing algorithms currently used by the Sentinel-3 satellite, to calculate water quality constituents like chlorophyll, which is an indicator of algae, and total suspended solids in the MBGL or upper MBGL lakes, and to revise, if necessary, current algorithms for chlorophyll estimates for the upper MBGL. So why is there this big difference I keep talking about? So to sum it up, in the upper MBGL lakes, in addition to particles coloring the water, there are areas with underwater plants where by the end of summer, the plants are just below the surface of the water. We also have floating marshy islands that provide a challenge. So we have a lot of different types of vegetation. And this image in the far right here is actually an underwater image. So it's the bottom of Lake Waterhen. We also have an algal diversity issue. So on Lake Winnipeg, Lake of the Woods, and Lake Erie, the lakes to the east of us, there's often these filamentous algae or long algae that form those grass clippings that you saw in the earlier image, or algae that can control their place in the water column are present. So those algae easily form those surface blooms, which are easy to see. Unlike the typical floating formations, the algal species in the other MBGL lakes is quite different in composition. The MBGL lakes have a very high diversity of very small, less than 1 micron, micro blue-green and green algae in both the north and south basins. This means that you cannot see the individual cells with the naked eye, and they look very different in the water column. So you can see on the left there that, I don't know if you can see in your image, but there's these very sort of, it looks like bubbles on the water, but they're actually these very globular forms of algae that are very patchy in nature. And on the top right there of the image, you'll just see examples of some of the different types of algae on these lakes, but there are over 40 different species on each of these lakes, and most of them are very small. So as I mentioned earlier, my research is part of the Manitoba Great Lakes program. And the Manitoba Great Lakes program is a large network approach to understanding the effects of climate, land use, and other man-made change to nutrient and carbon loading, and how it affects flow through the entire MBGL system. And this program consists of multiple sub-programs. And our projects utilize a variety of sample collection monitoring systems, including the in-lake, in-river, and in-watershed point sample collection and deployment of summer and winter moorings. So the moorings are located one in each of the lakes, and they are able to then collect a continuous record for algal concentration, oxygen, and a few other parameters. And through the work of the MBGL program, we were able to add our satellite remote sensing work by conducting some multi-year surveys. So to collect the water samples needed to compare to the satellite imagery from 2016 to 2017, my colleague and I conducted that open water sampling I was talking about on all 3 of the lakes to capture spatial and seasonal trends. So to go 3 times a year to collect sort of spring, summer, and fall representative samples. And you can see all this work had to be done by pulling our boat behind our camper truck, and that boat is 16 feet long. While water samples were collected and they were partitioned into particulate and dissolved fractions. So we filter the water to get what can stay dissolved in the water, and then we get to see what does not dissolve in the water and collect it on a filter paper. And we preserved samples for nitrogen fixation or biological analysis. We also did vertical profiles, which means we took a sample with an instrument to measure the water quality from the surface of the water all the way to the bottom, using instruments that could collect oxygen, chlorophyll, turbidity, temperature, and light. So this is a map of the lakes with all of the stations that we were able to sample on there. So in these images here, you can see us measuring water clarity using a Secchi disc and taking a surface water sample just by sticking my hand under the surface of the water. And that top right image shows how the samples look after they've been partitioned into those various fractions. So the dissolved water goes in the bottles and the particulates stay on these filter papers. So lakes Manitoba and Winnipegosis are mid-latitude cold climate lakes. Both receive water from multiple watersheds within this Nelson River Arctic Basin. And so for my work, I actually divided the lakes into 3 distinct basins, which we're not really going to go into here. But you can think of the lakes as having either south, central, and northern basins, such as Lake Winnipeg is often referred to, or more accurately in our case, south, northeast, and northwest areas. And just to give you an idea of basic statistics about the lakes, to give you an idea for water clarity, which is one of the constituents that are important to remote sensing, in Lake Manitoba, the deepest Secchi values were found in the North Basin with an average of 1.9 meters. So that means if you look into the lake, you can only see 1.9 meters down. And in the South and Central Basins, water clarity ranged from between 0.7 to just over 1 meter. All 3 lake basins in Lake Winnipegosis had a similar mean Secchi depth of around 1.5 meters. Though as you can see from my box plots here on the bottom right, there was quite a bit of variety when measuring those samples. So how do we know we're right about what we're collecting and about when we use a satellite to interpret an image? So now we know how satellites measure photons from the sun and convert that to digital numbers and into images. So what do we do after we have the images? Remember that we are looking at a representation of the algae as calculated by an algorithm. How do we know the values we get are correct? Before we can be certain that what the satellite sees translates accurately into a constituent value, we must analyze the water samples we collected. We can use this information to compare the concentrations we get from sampling the water to the concentrations calculated by the algorithm we used. In addition, we can use an instrument called an analytical spectral device, or ASD, which is shown in that image, to measure the spectral reflectance of the lake and simulate what the sun reflectance would be by using this white reference panel, which is at the top of the image. So the ASD is connected via a fiber optic cable, which is then put out over the water here. And on the bottom here is this white reflectance panel I'm going to talk about a little bit more. So the ASD allows us to view the same wavelengths the satellite will see without having to worry about confounding factors such as cloud factor, which have to be corrected for in a satellite. Other issues such as forest fires causing haze in the atmosphere can also cause problems with the quality of the satellite image we are able to download. And this is avoided when we use the ASD. So the spectral graphs at the bottom of this slide show the spectral absorption of chlorophyll on the right and the reflectance of chlorophyll, color dissolved organic matter, or CDOM, and water to the left. You can see that chlorophyll is green because it reflects strongly in the green part of the visible spectrum. And we can see sediment is brown because it reflects light in the near infrared, which is up higher to the 700 nanometer wavelength end of the spectrum. You can see that chlorophyll also strongly reflects in the near infrared, which is here, but we don't usually use that peak as any sediment in the water could interfere with our reading because it also strongly reflects there. So in this image here by Dr. Greg McCullough on Lake Winnipeg, just to give you an example of what a transition zone can look like when we move from turbid water to algal-filled water, you can see the change in the spectral reflectance as the sample sites move from the algal bloom on the top left corner to more muddy water on the right. So you can see that up here we have very high chlorophyll concentrations, and down here we have very low chlorophyll concentrations and very high turbid water. And this data was collected using a different satellite called, and then calculated using the AVHR algorithms. So if the conditions are going to be good, so there's no smoke or haze and minimal cloud cover and no wind is very important when you're in a very small boat on a lake, I would use the ASD, so the analytical spectral device, before and after we collected water samples to take spectral profiles of the water so that I could compare them with satellite images. I would start at a sample station and take samples every kilometer for a few kilometers. And as I said before, when we had the actual image up, there's a fiber optic cable attached to the device, the ASD. This is located to extend over the front of the boat and get out of the boat's shadow. Underneath it sits the white reference panel. I take a certain number of measurements over the white reference panel to act as a baseline to simulate the sun reflecting back from a pure reflective surface. Then I move the cable over the water where I take more measurements. I repeat this process 10 to 20 times at each site. And then just like a satellite, the data is saved as a digital number and then converted to radiance or reflectance values. And the image at the top left is just showing you what are the limits of a satellite compared to the ASD. So the satellite cannot see through clouds and it cannot see below the surface water, the upper surface water. So if the algae are at the bottom of the lake, a satellite may not see it if the lake is too deep or too turbid. So this is a summary of the results for one of my sample sites. This is a sample from the 12th of August, 2017. And you can see that the output from the ASD are graphs here on the left. And the sample site is circled down at the bottom on the right. And there's a whole bunch of dots at that one location because we did that transect that I talked about for my last slide. So one thing to note that between these two graphs, there's orders of magnitude difference. So this scale is a digital number that goes to 3,000, and this is a scale that only goes to 250. And they've both been converted to reflectances, which are percent values. So the bottom graph is the water, or the second graph, I should say, is the water leaving reflectance. So what the satellite sees when it's over the water, and the top one is what the satellite sees when it's over a pure reflecting surface. And you can see that our maximum reflectance occurred around 560 nanometers here. And the actual chlorophyll concentration in the water that time was around 15 micrograms per liter, which converts to 0.015 milligrams per meter cubed, which is a common unit used when talking about algae. So the highest chlorophyll concentration that I've seen in the Manitoba Great Lakes is around 28 to 30 micrograms per liter. So these present very different values than when a satellite looks at a bloom image, where chlorophyll concentrations, which is what we're actually measuring here, can reach 200 to 400 micrograms per liter. Now that bottom graph is a reflectance spectra by Anatoly Gittleson and colleagues from a conference proceedings, where we can see that their sample also peaked around the 560 nanometer mark. And they consider those samples taken from low chlorophyll concentrations, and you can see that they were in fact still a lot higher than ours, because their values are 5 milligrams per meters cubed, whereas ours would be 0.015. So the ASD also tells us which constituents are affecting sunlight absorbance or scattering. So if I saw peaks, as I go through my samples and look at the different ASD peaks, if I see peaks that come out over here and over here, if you remember our graph with the CDON and the sediment reflectances, if I see peaks that come out here, I'll know that there's probably more sediment or colored matter in the water that's causing reflectance. And so by looking at our ASD data, it can help us narrow down which satellite algorithm is going to be best suited for our type of water. And the image on the left is chlorophyll reflectance calculated using the same Sentinel-3 satellite image date as the samples were taken. So to analyze the data, I used software provided by the European Space Agency called SNAP. And in this case, I used the default algorithm, which is called the C2RCC processor, which is the Case 2 Regional Coast Processor Color Tool, which is measuring what's called the MCI, or the Maximum Chlorophyll Index, which is an algorithm developed to measure maximum chlorophyll line height. And you can see in this instance that even though you can't see the south end of Lake Manitoba here, it did not perform well compared to the values that I see as I get into higher concentrations. At lower concentrations, it wasn't bad. And this image on the bottom right is just showing you a comprehensive review by Odermatt et al. Of all the different types of algorithms that have been used to calculate constituents like chlorophyll concentrations from satellites. And those are what I will be using as bases to perform the analysis on my data for deciding if one of these is going to be best fit or not. So what's next? So in summary, the Manitoba Great Lakes are optically complex waters. More than one lake needs to have in situ water quality compared to satellites to ensure satellite algorithms are accurate. And the upper Manitoba Great Lakes are complicated by the diversity of algae, submerged vegetation, and particles in the water. So for me, what's next is continuing the analysis. This table here just shows you all the different types of constituents that we can measure either via the actually in the water or via the water and by satellite. So we can make those comparisons and find the best algorithm we can to use satellites as a way to remotely monitor our lakes. And I would just like to dedicate my presentation to my thesis advisor, because this is also part of thesis work I'm doing, David Barber, who recently tragically passed away. And I'd like to thank you for sitting through my presentation.